Welcome to homework.
Once again, we have a new problem. It's still on a single slit experiment, and we're dealing with diffraction grading in this particular problem. Remember, single slit experiment are such that they have one opening right there, and so if there's light coming through, you expect diffraction to happen on the opposite side, where most likely you're going to have a screen. So on the opposite side, you're going to have a screen. So this is a single slit experiment. And when we think about orange light, the wavelength lambda is given as 600 nanometers, and then also this is a minimum intensity. If you think about it, when you reflect light, there's always going to be intensity coming in. And of course, also we do have a blue light. We can have the same diffraction grading, and then assume there's blue light coming through, and its wavelength this time is given as 500 nanometers in the same particular problem. The angle that they're coming in is really small, so we might change the angle a little bit, tilt it just a little bit. So there's an angle going on right here. So we're going to tilt that. It's a small angle. We're magnifying the whole thing. So assume there's an angle right there, and you can call it theta if you want to call it that. So the angle theta is 1 millirad, and that you can change it to 1 times 10 to the negative 3 radians. Those are the pieces of information that were given in the problem, and our goal is to find the minimum width of the slit. That's our goal. If you see this as your slit, then we're asking what's going to be the minimum of that one. When we start with the orange light, we know that the minima condition is given by d sine theta equals to m orange times lambda orange. You want to think of that, where d is the slit width. D is going to be our slit width, and theta is obviously the angle, m is the order, and lambda is the wavelength. And in this case, we're dealing with the orange wavelength. If you recall, it was given as 600 nanometers in the previous page. When it comes to the blue, and this is the blue light, when it comes to the blue light, or we're calling it the blue-green light, we want to call it that, just going back to clarify that this is the blue-green light. It also has its own conditions. So d sine theta equals to m blue-green times lambda blue-green, just to be super specific about that. And so from these two equations, we realize that the d and theta are the same for both of them. So it means these two equations are equivalent. These two equations are equivalent. So m, as you can see, d sine theta and d sine theta is consistent for both equations. So we can rewrite this as m orange, lambda orange equals to m blue green, lambda blue green. Since the equivalent, because of d sine theta is the same for both of them, and so we can divide both sides by the blue-green order on both sides. That's the order. And then also we can move the orange lambda on the other side by dividing both sides by the wavelength of the orange intensity light. And so in the next page, we get to see that we can do a substitution based on the information that we're given. So m orange, all of m blue green. Those are the ratios, the orders for the minima is given by going back. You can see this is 600 for orange and 500 for blue-green. So we're going to have, in the equation, they kind of like flip, since if you cancel these out and then cancel those out, we have blue-green at the top. So we're going to have 500 nanometers at the top, and then below we have 600 nanometers. So it's 5/6. Those are the two ratios from the expression. And so if we know that d sine theta equals to m orange, lambda orange, we can tell that d is equivalent to m orange, lambda orange, all of sine of theta, and that means that the m orange is 5 and m blue green is 6. So we're going to use 5 in this equation, and then the wavelength of orange is 600 nanometers, and we want to change that to meters. So that's 10 to the negative 9 meters of nanometers of a single nanometer. We want to see that, and then the angle is theta. The angle is theta, so we're going to see that if we shift the angle for theta, we have 1 millirad times 10 to the negative 3 radians, all of a millirad. So those are the pieces of information that we have in this particular problem. And so the minimum width, if you simplify that, the minimum well, this is sine right here. So the minimum width turns out to be 3 millimeters. So once again, in this problem, we had we're given the wavelength of the orange light intensity and then the wavelength of the blue-green light. We used those two ratios and the minimal condition to find that the relationship between the minima of orange and the minima of blue is a flip of the wavelengths, lambda blue-green over lambda orange, and then we move ahead and found out that the minima for orange is 5 and minima for blue is 6. So we're going to pick up one of them, and then we get to simplify the problem and see that it's 3 millimeters. So hope you enjoy the problem. Feel free to send any questions or comments, and have a wonderful day.